Okay, thank you.
I don't have to leave, Professor.
All right, that's fine. All right, this type of problem that I just had, the quiz problem number 2, is called the limiting reactant problem. And the situation is like this. Let's say you have enough mix to make 100 pancakes, and you have enough eggs to make 10 pancakes. So if you have enough flour to make 100 pancakes and you have enough eggs to make 10 pancakes, will you make 110 pancakes? Could you? No. No. How many pancakes could you make?
10.
Just 10. 10 is what we call the theoretical yield. And so what happens is a lot of people, they come up and calculate from the 4.2 pounds of methane, people were saying they could make 11.5 pounds of CO2 or so, right?
Yeah.
But from the 50 pounds of air, you're only getting 7.5 pounds of CO2. And so if we have 7.5 plus 11.5 makes 18, 19. Would we get 19 pounds? No, it's the same situation. In theory, we could only make 7.5. And so that's what we call the theoretical yield. And so let's take a look at limiting reactant problems in general. In stoichiometry, these are the most common calculations that we do. Using limiting reactants. And when you're working in the lab, you're doing this all the time because you want to calculate how much of each is required, and you typically want to add a little bit of excess of one. All problems are limiting reactant problems in chemistry because the problem is this: we can't weigh things down to individual molecules, and so we're always going to have a few extra or more than a few extra of one or the other. And so limiting reactants, the reactant that is first totally consumed in a reaction determinant is the limiting reactant. It determines the maximum yield. The maximum yield possible is not the biggest yield. The maximum yield possible is the theoretical yield. This is the maximum yield you can get given the conditions of reagents you have. Then we're going to have an excess reactant. The excess reactant you have too much of, and so it's going to waste. This is the bottom part, skip that. And so here's an example of limiting reactant. Here they're taking atomized carbon atoms here. You can get these vaporized graphite or something. You get carbon atoms in the gas phase like this. They're going to react with CO2. And so if I have reacted with O2 to form CO2, sorry, here's the reaction. Carbon plus O2 yields CO2. If I have 3 carbons, I can make 3 CO2s. However, if I have 2 O2s, how many CO2s can I make? Only 2. And so I don't have enough O2. I have more than enough carbon. So the O2 is going to be our limiting reactant. And I'm only going to end up with 2 CO2s. One of the carbons is going to be left over. That's unreacted. So this is excess limiting and theoretical yield. So the theoretical yield here is 2 CO2s. Here they're summarizing it in the table. So they have 3 moles of carbon, 2 moles of O2, 0 moles of CO2. And then they're going to react it. It reacts in a 1-to-1 ratio. So we're going to lose all our limiting reactants. So we lose all 2 moles. It goes to 0. But we're only going to lose 2 out of the 3 carbons. So that leaves us with 1 left over. Here's our theoretical yield. Here's our excess. The amount of limiting reactant left over is always 0. The limiting reactant is always 80% chemical reaction. So how do we solve these types of problems? We have to do 2 separate ones. There are 2 ways we could solve this problem. Let's see, solving the limiting, this is the comparison of moles method. The comparison of moles method is like taking a look at this table. Let's look at this table. know we need these in a 1-to-1 ratio, so when we compare the moles given, we need these in 1-to-1 ratio. We got too much carbon, not enough oxygen. Let's comparison of moles. I don't like comparison of moles method. I like the smaller amount method. The smaller amount method is this. The reason I like the smaller amount method is because we got to do this calculation anyway. And so that's comparison of moles, which I'm going to completely skip. I'm going to skip this. Skip that. And then go to this. This is the way I like to solve these problems. The smaller amount method. Which one yields a smaller amount of product? And so we do stoichiometry calculations. For each reactant, we do an individual stoichiometry calculation like this to figure out how many or how much product we can form from each. And then we pick the smaller amount. And so calculate the amount of product that can be formed by the initial amount of each reactant as a separate problem. Ignore all the other reactants. Reactant that yields smaller amount of product is the limiting reactant. Smaller amount of product is the amount that will be formed when all the limiting reactant is used up. And this is called, what was this called again? The amount of product that can be formed by the limiting reactant is called the blank yield, theoretical yield. Okay, this is an extra bonus calculation. Calculate the amount of excess reactant that is used by the total amount of limiting reactant. Subtract. And so this is the amount of excess reactant that remains. Let me show you how we do that. This particular calculation. Setting up that last calculation, the amount of excess reactant remains. So in this particular example here, which one was the excess reactant? The methane. And so in this particular example, we want to figure out how much methane is left over unreacted because all the O2 in the air has been consumed. There's no more O2 left. So here, amount of excess methane remaining unreacted equals the initial amount minus the amount consumed by the limiting reactant. This is a new stoichiometry calculation here. And so we do this via a new calc. And so we could do this for this particular problem here. If you haven't finished this problem, continue working on it. But what was the initial amount of methane? 4.2 pounds methane. Some of that's going to be left over. Now, how much is going to be left over? Well, we got to calculate how much was consumed by the limiting reactant. And so, what was the limiting reactant again? The limiting reactant is 50.0 pounds of air. We didn't have enough air in here. You know, this is an enclosed container. Worry about it. Well, 50 pounds of air is going to consume how much methane? If all 50 pounds of air react, how much methane is consumed? Well, that's a stoichiometry problem. So what we need to do is we need to get to moles. And so we're going to go from pounds of air to maybe grams of air. And so in 1 pound is 453.4 grams. 453.6. And then where? Yeah, grams to moles. So we just figured out the molar mass, 29.4 grams of air in a mole of air. let me just take a quick side detour here since this is working now. Let's try this. I tried this earlier. This is the composition of air here. Actually, I'm off. Air is 78.09% nitrogen, 20.95% oxygen. So it's 21%. 0.93, almost 1% argon, 0.039% carbon dioxide, small amounts. Air also contains a variable amount of water vapor, on average about 1% at sea level and 0.4% over the entire atmosphere. This is the composition of air. Well, based on that composition, what is the average molar mass of air? So we could figure that out too. The average, actually, we don't even have to figure it out. Average molar mass of air. Well, my calculation's way off a bit, but it depends on what you have as the composition. The average molar mass of air is they get 28.8 grams per mole of air. But we're okay. I mean, we gotta keep in mind that air is a variable mixture, so it's not the most accurate, but it's all right. We're just gonna go with it. So we already did already. And so once we go to moles of air, then where we're gonna go? Where can we go? From moles of air, we can go to. Well, we can because this is 20. Yeah, we can only go to moles of O2. So we're going to go for 20 moles of O2 for every 100 moles of air. That's just because of the percentage of, there is a percentage for CO2, but that's a different CO2 than this. That's the CO2 that naturally occurs in air. Okay, now we can go to moles of CO2. Or are we going to moles of CO2? No, we don't. We're not going to moles. Where are we trying to go? We're trying to go to CH4. Right? And so how do we get from moles of O2 to moles of CH4? What's the mole ratio? 2 to 1? All right, so 1 mole of CH4 for every 2 moles of O2. Is that correct? And once we get to moles of CH4, then we can go to grams of CH4, 16.05 grams of CH4 per mole of CH4. And then from grams of CH4, we could go to pounds of CH4, 1 pound over 453.6 grams. Okay, and then that takes us, what we end up with here is pounds of CH4. That's the pounds of CH4 that was consumed by 50 pounds of air. And so let's figure out what that number comes out to. So it's going to be 4.2 pounds of CH4 minus how many pounds of air. So I'm going to take 50, oops. So take 50 times 453 divided by 453 is going to give you the same. So 50 times 20 times 1605. Okay, divided by 29.4 divided by 100 divided by 2 divided by 4 equals. So I get 2.729 pounds of methane consumed. Okay, minus 2. So 1.47 pounds of methane will be left over. So about 1.5 pounds will be unreacted. Does that make sense? So that's what we have for limiting reactants. Okay, so let's take a look at number 74 here. Baking cakes and pastries involves the production of CO2 to make the batter rise. For example, citric acid, which has the formula H3C6H5O7, in lemon or orange juice can react with baking soda. Baking soda, what's this called? The name, chemical name of baking soda. Sodium bicarbonate or sodium hydrogen carbonate to produce carbon dioxide gas. So here's the reaction here. So we take our citric acid and it reacts with the baking soda, the sodium bicarbonate, to produce this. What's this called here? This is actually called sodium citrate. This anion, it's the anion from citric acid. Sodium citrate plus 3 CO2 plus 3 water. All right, question A. If 6.00 grams of citric acid reacts with 20.0 grams of sodium bicarbonate, immediately I'm thinking limiting reagent. You know, I don't know which one. You know, I'm given 2 ingredients. I don't know if this is stoichiometric. I have just the right amount. It could be. This could be just the right amount of citric acid to react with all this. But more than likely, we have too much of one. If you're going to have too much, what would you rather have too much of in your pastry? Would you rather have too much citric acid, or would you rather have too much sodium bicarbonate? Which one do you think tastes better, citric acid or sodium bicarbonate? If you're going to have it, what would you rather have? Like lemons are 80% citric acid, so. Kind of a lemony citrus flavor, or a powdery, I don't know, pulverized rock flavor. Powdery pulverized rock flavor, or a citrusy flavor. What would you rather have more of? I'd rather have more lemony. I'd rather have a little bit of extra citric acid than sodium bicarbonate. But I don't know. Maybe they got it mixed up. You know. But we don't know, because, you know, and who wants to spend the time to weigh out everything so exact? You? Nobody does. Nobody wants to get the stoichiometric because it takes too much time. And not only that, you're going to be unsuccessful to get it at the particular level. And so we always do. All chemical reactions, all chemical mixtures are, we think, which one would we rather have left over? We're always going to have a little bit of leftover of something. Hopefully it doesn't contaminate our product. Well, this one we can't clean out of there, so it's going to contaminate it. So I'd rather have it contaminated with a little bit of residual citric acid. But I don't know, which one is the limiting reagent? So did they might have chosen sodium bicarbonate, which is this pulverized rock, basically. And so can you do this calculation and see which one is the limiting reagent, just as an additional example? Maybe it's too much for the limiting reagent, but the reason I want to do another one of these is because limiting reactant problems are big. I mean, this is one of the main calculations in chemistry that everybody does. I shouldn't have named it for you. Should have been able to name it, I guess. Because the ic acid tells you the name. You know, if it's citric acid, the anine's got to be called citrate. And then B, what mass of which reactant will remain unreacted? So we won't do a quiz for this one. Just do it in your book, and then let's take a consensus.